the sun, and there's 3 layers in the interior of the sun, there's 3 layers in the exterior of the sun, and this is actually the exterior of the sun's kind of like the sun's atmosphere. It starts with the atmosphere, we say kind of starts with the photosphere, and then the chromosphere, and then the corona, kind of. So this is closest to the sun, and then we have this one, and then we have the corona, and the corona is what we see during an eclipse. Yes?
Why does the graph go down right at the beginning and then back up?
Yeah, so that actually...
Because it says height in solar atmosphere.
So this is the height, so that means how far it is. That's kind of like, so that's closest to the sun, that's farthest from the sun. But what's along the x-axis? Or sorry, y. This is y. What's along the y-axis?
Oh, the temperature.
Temperature, yeah. So which one, photosphere, chromosphere, or corona, is the hottest? The corona is the hottest. And I think I might have said the other day, it's the outermost layer of the sun's atmosphere, but it's the hottest. Isn't that crazy? I know. Although heat has to do not only with temperature, but it has to do with mass. And the corona is like the least dense. So there's not a lot, it's a lot of thermal energy out there, but it is the hottest. And so to answer your question, why is it so hot? It has to do with, I think, the electromagnetism, so that the hot particles are kind of trapped there. But it is the hottest. Okay, so I'm going to play this video to kind of show you, to animate this thing called spicules. So spicules, where does it say? Spicules are in the corona. So remember the corona, so it goes photosphere, corona, photosphere, chromosphere, and corona. So corona is the outermost. So can you see these? Search letter G. What did we say that the little kind of little honeycomb looking features on the sun are what? Call them? Not grains, but granules. So you can kind of see some granules here. And I don't know if there's any speech to this. You'll see the spickles. Now, in the next part, and I have slides to hand out for that too, handouts. The next part we're going to talk about when the sun is normal versus when the sun is abnormal. When the sun is abnormal, we call it active. So when it's normal, I want to emphasize this. When it's normal, we're going to see granules. Okay, those are kind of beneath the convection. On top of the convection, the interior of the sun. And then normal, we're going to see spicules. Okay, so you have to kind of compare that here in a minute to abnormal or active. So I think the last one I've got to show you, and I think I will go ahead and show you this little video too, about a comet. You're like, what does the comet have to do with the sun? Well, I'm going to show you here in a minute. But this video is showing you again what the sun would look like. Now you're like, well, where's the sun? Where's the bright middle? Well, on purpose, some telescopes, if they want to see the edges of the sun, they have to block or mask the sun. So that's kind of what you're seeing, a special telescope just for the sun. And it's showing you kind of what the coronal regions would look like. So here's that. Okay. Well, I've been trying to kind of warn you that the sun has kind of 2 phases, and it kind of has in between. It doesn't go abruptly from being quiet to being active. It kind of ramps up. So things of a quiet sun include some of the things we've talked about. Solar wind, always there, quiet or active. Granules, those kind of creepy looking things that are on the surface of the sun, always there, quiet or active. Super granules, I didn't talk about much, but super granules, I don't know if it's in my notes, but they're kind of like blobs of the photosphere, chromosphere that lift up. Okay, those are super granules. We talked about spicules, always there. Okay. So what's not always there? Well, this list in bold, if you have your slides, you want to put like a little star next to it, you can, because I'm sure when I'm putting together your Unit 3 exam, I'm going to say, hey, what are features of an active sun? So this part, I might not spend a lot of time, but I'm going to kind of show you some of these pictures of what's associated with an active sun. When the sun lines up, what do we got going on? We have sunspots, plages, filaments, prominences, coronal holes, and the big granddaddy of them all, this is the one that we kind of look for, this last one, the CMEs, to basically destroy our electrical grids okay, coronal mass ejections, okay, but they're all features of an active sun. So we talked a minute ago how the corona is the hottest layer of the sun's atmosphere and it's the outermost. And I think what I tried to explain is part of the reason the sun has these cycles of being active and being quiet has to do with, like you can see on this point, the sun's magnetic field. Okay, crazy magnetic field. And that also is why, as I understand it, the corona is so hot. So when I keep talking about these cycles, is it active? Is it quiet? Is it active? Is it quiet? So here's the deal. This would be active, active, active. This would be quiet, 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 quiet. Okay? So what you're looking at on the y-axis are sunspots. And sunspots are, I don't know if they were on my list a minute ago, and I had to make a little star next to it. The presence of sunspots or the absence of sunspots are an indication of whether it's active or whether it's quiet. No sunspots, quiet. Lots of sunspots, very active. So these are showing you sunspots, and if you were to kind of go from peak to peak, kind of like a wavelength, you would probably get about 11 years. So the peaks are about 11 years apart. So I mentioned 2018. So 2018, you're about out to, let's see, that's 2020, you're about out to here. These low activities we call minimums. So I'll put MIN there. Solar minimums, MIN, makes sense. Ooh, wow. Go back. Okay. MIN. And then these guys right here are maxes, MAXs. Okay, so the peaks are maxes. Now notice like the peak, this is what we call we're at the end of cycle 24, but the peak for cycle 24 wasn't near the peak for cycle 23. Okay. So, you know, science, Mother Nature is messy. Does it always follow the same pattern? No. So we have some kind of differences here. So space weather is probably most concerned or comes into play when the sun's active. A minute ago, we kind of looked along the y-axis and that was the number of sunspots. These are sunspots, but actually, to me, I see more than one. So this is probably a group, what we call a sunspot group. Sunspot group. And there's a miscellaneous sunspot over there. I think I showed you just a little bit of some eclipse footage. It was the, yeah. And it had a sunspot on it. Okay, there's a close-up. Aren't those cool? The other day when I told you granules, like those kind of creepy looking things that are always there, were about the size of the Earth, I probably overstated their size because to me, they're showing relative to the disk of the sun, that's kind of how big the Earth is. Remember you guys did that lab a while back where you had the cute little sun and I drew the cute little Earth and I drew the sun on the board, so that's probably that. There's a close-up of the sunspots. These dark regions are actually cooler regions on the surface of the sun. You can kind of see the granules. This is showing you, this is reinforcing the fact that, I don't know if I mentioned it before, but this, I think I did. The sun actually spins on an axis of rotation like a planet. It takes about a month for it to complete one spin. It has what we call differential rotation. So the poles, I think, are moving faster than the equator. Can't remember. But you can kind of see the sunspot group kind of go around. Now, sunspot groups will come and go. They'll fade in and they'll fade out. Sunspots will come in and they'll fade out. That's kind of a crazy little blemish. The problem with sunspots is if you have sunspots, you can have all of those other nasty things, like solar flares, prominences, plages, coronal mass ejections, okay? This is looking at the sun when it is in an active phase. Now, this is the difference between the previous picture and this picture of the sun. The previous picture was in kind of mostly visible light. This is in X-rays, I think. Okay. This is in X-rays. And it's trying to show you, it's hard for me to kind of see it, but it's showing you this feature called a coronal hole. Coronal, meaning corona, right? The outermost layer of the sun's atmosphere. And I kind of think of coronal holes as kind of, I read they're kind of like almost conduits that go through the star, that go through the sun a little bit. This is looking in a different sort of energy. Let's see, that only fits, that only gives us light that's produced by the presence of the element calcium. Symbol for calcium, of course, is Ca. So this is kind of showing you more of a subdued picture, trying to show you some of kind of the activity that's going on. I'll circle the word here. Plages, which I had you star a little minute ago, are features of an active sun. And plages are kind of, they look kind of like, let's see, plages, filaments, they look kind of like a line. This one looks kind of scary. This is a prominence, and actually a prominence you can only see if they're kind of edge on like this. A prominence edge on would look like a filament kind of face on. Does that look scary? I think so. So if it kind of looks like that material, I'll go circle what material I'm talking about. If it kind of looks like this could actually lift off and take off, maybe, maybe not. Depends on how much energy it's ejected with, and it depends, we figure gravity is trying, the sun's gravity is trying to keep it with itself. Picture of a solar flare. So you can kind of see the little, solar flares are little burps, coronal mass ejections are big burps. Flares can be disruptive too. So if that's the sun, okay, if the flare occurs on, and I'm the Earth, if the flare occurs over here, if that burp's over here and the Earth is over here, I'm okay with that. But if this is the sun and the burp appears over here or occurs over here and I'm the Earth, that's a bad thing, okay? So that would be space weather. We're concerned with those solar flares. Solar flare associated with sunspot group. Now, I told you the granddaddy of them all is the CME, coronal mass ejection. Right? So CME. It's hard for me sometimes to tell the difference just looking at these, and so I wouldn't give you like a picture on a test and say which one is the granddaddy and which one's just the right. But the coronal mass ejection is large. The ejection part of a coronal mass ejection is that material from the sun successfully escapes the gravity of the sun. Okay, so if this is the correct scenario where the Earth is in line with the burp, if it's a coronal mass ejection, that could be a bad thing. And I mentioned power grids going out and all that. I don't think we've had a direct hit with a coronal mass ejection since back during the telegraph eras. And so there are videos out there, documentaries that will talk about that particular burst or burp that the Earth got, and it brought down the telegraph system. A few years ago, maybe 10, 12, maybe now, by now, but there was some solar activity that brought down power lines in Canada. Now, this is the Earth right here, okay? So I don't know if you can see that little circle there. That specifically is the Earth. If you see this blue region, that's part of the Earth's protection. That's actually what we call the, what is it called? That is our magnetosphere. That's our magnetic cocoon that's created by the Earth spinning. Okay, so that blue thing helps deflect charged particles. It does to a certain extent. All right, so sunspots groups. Okay. So this is the same solar activity, kind of looking at it in different ways. Here with this coronagraph, where you can see the sun masked out, you can see the burp, kind of the lines of energy. Here you can see really see the lines of energy. Different, and this is a good example of looking at a star at different wavelengths, different energies. We're going to look at other stars with different energies too. different colors of light, different wavelengths. And angstrom, if you ever see angstrom, all an angstrom is distance. So it's talking about wavelengths. So that's what the angstrom is. So this would be the shortest wavelength. This would be the longest wavelength up here. And this is looking at in a picture of like the magnetic energy that the sun is putting out. Just different ways to understand what's going on. This is activity associated with, I'd have to double check that kind of sun cycle thing we looked at, but 2012 was, I think, maybe near solar max. Okay. So space weather, solar weather, that's what we mean. And like I said, that actually the cycles, the solar cycles, you get lots of sunspots, not many sunspots, and then lots of sunspots about 11 years apart. All right, what do we mean when the sun is being active? And actually this was the information I had to put a star next to. Well, if the sun's being active, you can expect lots of sunspots. Sometimes those sunspots are groups, sunspot groups. Solar flares, it's the little burp prominences kind of on the edge, filaments on the and plages, coronal holes, the conduit, coronal mass ejections, the granddaddy. So it sounds kind of almost cold, okay, but okay, there's the sun and here's the earth. We're like, who cares what the sun's doing, right? Well, one thing I already mentioned that if a coronal mass ejection occurs at the wrong place, it can bring down our power grids. Actually, I'd get you guys to buy this here on Earth. If we know it's coming, there is stuff we can do to kind of mitigate the damage. In a minute, you're going to see, is it coming up? Yeah, but what does that have to do with anything? So that's an asset to the world, actually. That is the International Space Station, the ISS, which won't last forever. But right now, there are astronauts going up to there and astronauts coming home. And we've actually talked about how do they do that. And remember we said, well, we used to have space shuttles that do that, and now we catch a ride with the Soviets. Oh, sorry, the Russians. And then they had a close call, remember, kind of recently. The Russian spacecraft had to eject the astronauts out. But anyway, my point is, if that's up in outer space and which it is, and the sun does a burp, what are we going to do? Well, if we know it's coming, we have a little bit of warning, we're going to try to mitigate the damage to the International Space Station. Even more importantly, we're going to try to mitigate the damage to our people assets. You know, assets sound, like I said, it sounds so cool, but we care about those astronauts up there. And a dose of, even a flare, a good solid flare, let alone a coronal mass ejection, those charged particles could really damage an astronaut up there. I know they have spacesuits, but they're not rated for that much energy. So, this is another thing. This is called Northern Lights, okay? And the word northern kind of gives it away. If I had the globe in here, this is Earth in my hands, and at the North Pole, and actually at the South Pole, is a place where charged particles can kind of cascade if the Earth is getting dosed with charged particles from the sun. So if we're on the Earth right here, we need to look north and hopefully see in our sky kind of this sort of phenomenon. Anybody see Northern Lights? On your bucket list. Okay. So if you want to see Northern Lights, what you need to do is make sure the sun is active, because that's dosing our atmosphere with charged particles that can make this glow. So we'll see one of these days. This is just kind of showing you little snapshots of the sun going through 1996 to 2006, which is 10 years. Those kind of bright spots, think of them as, we talked about coronal holes. I think of them as coronal holes, which means that the sun's being active. To me, when I look at it, you know, 2001, according to this, looks kind of active, which would be, if you take 2001 plus 11 years, you get 2012-ish. So that was another maximum. So it's quiet and maximum here. So this is showing you way back in the 1750s to sort of nowish, okay? This would be sunspot cycle 24, and we're actually kind of in the downward area. where again, along the y-axis is sunspots. So that's how we kind of track our cycles. The caption here, and sometimes I include it on my test, so I'll go ahead and circle it. The caption here talks about something called the Maunder minimum. And I've heard it called the Little Ice Age. And it's most notable in Europe, and it corresponds to kind of this region where there were few sunspots. And if there's few sunspots, sunspots, like I've been trying to describe, are an indicator of all the other crazy stuff you'll get with an active sun. So I know I said that sunspots, those darker regions, are cooler regions, but as it turns out, when the sun is quiet, doesn't have those cooler regions, actually, I can kind of think of it, it's not burping and stuff. So if we're over here on Earth, we're actually getting slightly less energy from the sun. So we can go into cold phases like that. All right. So we've been talking about the sun's magnetic craziness. And just to understand a little bit about magnetic stuff, magnetism, we could create magnetism right here and right now. A good way, I've seen it done, over here, this is physics stuff. Yeah, well, I'm not going to do it, but I don't want to. I have respect for electricity. Okay. So, this doesn't have a cord, but if it had a cord, okay, what we could do, you guys see the copper wires. So all we got to do is plug it in. And we plug it in, and when you plug anything in, basically it sends a current of electrons. So I would have electrons come through my cord, and they would go through this coil, and then they would go through this coil, okay, and they would complete the circuit, because that's kind of how they do. I don't know how to plug in, but the electrons would come in here, move, and go out. But it's their movement, the electrons moving. If this was on, and I checked for magnetism in the middle, it would be highly magnetic. So all you have to do is get charged particles moving, and that's the movement. Charged particles moving creates magnetism. Isn't that crazy? So the thing about the Earth is, you guys probably know there are no dinosaurs at the center of our Earth, right? Okay, good. But if we were to go from our Earth's crust inward, we would hit a liquid layer. The liquid layer on Earth. Well, that liquid layer actually has a bunch of iron. Well, the symbol for iron is Fe. And that Fe, some of those particles are charged. So as the Earth kind of spins around, those charged particles spin around. So those charged particles in the liquid part of the Earth's interior, actually create that kind of protective thing I showed you a minute ago, that magnetic field. So if you go outside the Earth, take your little magnetic finder, you would actually find a magnetic field around the Earth. I think that's kind of cool. This is all to say that the sun has a crazy magnetic field to it. Why? Because the sun is made of plasma, which is just charged particles. So here we go. This purple right here, this says magnetic fields trap gas. So actually, that purple thing is a magnetic field. What's it coming out of? It's coming out of a sunspot. What's it going into? Another sunspot. Okay? Now here's the deal. That totally reminds me of like playing Twister. You know, if you're playing Twister, you say, put your left hand on red. Put your right hand on blue. Okay? Put your right foot on purple. Put your left foot on yellow. So what I've just done is kind of twisted myself up. The sun is spinning. Okay? So kind of related to this 11-year cycle, what happens is this. So this is a clean slate. I'm going to show you 3 figures here. The first one is a new twister board. New twister board. This one is a twister board after a little while, and this is a twister board after even a little longer. I mentioned that the sun, I think I was right. I mentioned that the sun moves faster at the poles than it does at the equator. And so you have these cute little lines that are leaving one sunspot, entering another sunspot. But those lines kind of get twisted as the sun rotates. So it gets more and more complicated. And then my thing is that, you know, on Twister, how you fall down, and eventually everything snaps. And when it snaps, that's when you begin the new cycle. So that's kind of how those work. I usually tell students it's just the magnetic lines get twisted over time, and they eventually snap. I've heard it described kind of like a rubber band. All right, on to the next part. Yep. Yeah, I'm digging this, giving you guys the slides. But still, if you have questions, let me know. Now, for this part, I'm going to give you actually a sky map for October. You're like, this is nice. Like, this is the last day in October. Well, I really like it. By the way, it's kind of smaller because it only does what I tell it to do. I have it like at 60% or something like that, maybe 80%. So this is the sky map, and I probably gave you one, but I want to give you another one, which is a little bigger. They don't have the November one up. Was going to be my point. So we're done talking about our star, but hopefully keep in mind when we talk about our star. And now we're going to talk about other stars. And this is all going to focus on how bright is that star. This month is that last month. August, yeah. Or keep it till next August because it should work next August. Except for the planets. Yeah, the sky maps I give you, like the one I just gave you is for October. And next October, so it's October 2018, you can pull it out, October 2019, smile and say, well, it should work except for the planets. So we're just going to focus on how bright is a star. And we're going to see that there are a couple ways of looking at how bright a star is. So this is, we talked about star trails before. Isn't that beautiful? One of the things we talked about clear back in Unit 1 is that the stars actually will move over the course of the night. So I still got, I'll put my watch, so I still got 7 minutes. So stars will move over the course of the night. If that's Polaris, they will move counterclockwise. Okay? So stars also have different colors. I kind of see some blues there. I see some, so we have blues here. We've seen red stars out there at night. And this bullseye, this would be, if this is in the northern hemisphere, which I think it's in the southern hemisphere, but if this is star trails in the northern hemisphere, right where my dot is, that would be Polaris. So these are stars. I feel like we're turning a curve here in Unit 3. We talked about our sun, now we're kind of leaving our solar system, looking outside ourselves, hopefully even more than we have so far. And if you look, this would be what I call like a photo where somebody with their camera left it open for a while. Because if you look anywhere, you're not going to see all that stars. Actually, when we were out for a lab, we looked at the constellation Sagittarius. That has the Astros and the teapot, remember? It's kind of the archer. So you're not going to see all these stars. But in this field, you can see different colors and different intensities. And we'll talk more about those colors and intensities as we go on. So how bright is it? Well, in order to understand how bright it is, the two different ways of describing brightness, we need to talk about something called luminosity. To me, luminosity makes sense, and I think this little image shows it. Luminosity is basically how much energy it's pumping out per second, measured in watts, like your light bulb has watts. That's called the luminosity of the star. Now, the sheet I gave you, so I gave it to you, but again, I apologize, it's kind of small. But the side that has, read. The side that has the picture with the stars, if you look down here in the corner, it says how bright is the star. And way back when we first started talking about these star maps, I think you guys intuitively said, and correctly so, that the bigger the dot, the brighter it is. So keep that in mind, okay? This is what we call the apparent brightness. So this is how it appears to us. Now here, in a minute, I'm not sure if I'll do it in here or when we pick up again on Monday, Friday by we'll do something, not sure where. So Friday, if you're like, I don't know where we are, well, just come on down to this area and I'll let you know where you need to go. But the thing is there's another scale, not how bright it appears to us, but if you were to visit the star, how bright is it? Okay. Here's another thing, and I have some examples to kind of show you. But the deal is the farther we get from the star, the dimmer it's going to be. So I'm switching up. This is not the sun. This is just any beautiful, awesome star. What this is showing you is, I guess I could do it this way. Of course, AU stands for an astronomical unit. That's the average distance that our planet is from the sun, but this is just a star. So if I was 1 AU, it would be that bright. If I was 2 AUs, it would be that bright. And if I was 3 AUs, it would be that bright. So here's the deal. I kind of like this. It actually is trying to show you that each step means that that same shaft of light is being spread over a larger area. So here we have 1 box, here we have 4 boxes, and here we have 16 boxes. Okay, so it's diluted. It's diluted, you know it is. Okay, so here's the deal. The problem we have with looking at a star and gauging how much energy it's putting out is that the distance is a player. The distance is a variable as to how bright it's going to appear to us. So we actually have to remove the effect of the distance to understand how much energy it's putting out. Let me check my watch. Still got a couple minutes. All right. So there's different things in science where I say, what's your clock? 46. This is one of the places in science where I say, don't blame me, because there's things in science where I'm like, I wish they would have done it a different way. Here's the deal. I'll go ahead and draw it up here. Yeah. If you look at the scale, the thing I just gave you, it might say it, I don't know. So this is, I'll put this +6, and I'll put this 0, and I'll put this a -6. Okay, this is dim, very dim. And this is, I'll put V for very dim. This is very bright. It just is. It just is. And actually 0 is pretty darn bright too. But do you see the problem here? The more positive it is, the dimmer it is. Totally. So there was a scale developed a long time ago. I call that a long time ago. And it said that basically the brightest star these folks saw, they called it +1. And the dimmest star these folks saw, they called it +6. And we kept that scale. The thing is, for every, we call these magnitudes, like a +6 magnitude, a 0 magnitude, a -6 magnitude. For every 1 unit, that's actually a factor of 10 times brighter, 10 times dimmer. For every 1 unit you move over. Okay? So a -1.46, very bright. Okay, a +3, very dim. Relatively dim. So, here we have some things you might see in the nighttime sky. So the faintest object you can visibly see with your naked eye was a +6. Polaris is running here. Alpha Centauri. Check this out. Jupiter, Mars, Venus at its brightest. Full moon, the sun. Never look at the sun. Okay. Dim things we have over here. Very high positive numbers. If you have a nice large telescope, this is kind of the plus magnitude you would see it at. The Hubble Space Telescope, it's not on here, but you can kind of hopefully get a sense for that. So we'll kind of, I just want to kind of leave you with this, where this, we'll pick on Orion a lot. Constellation Orion here, and also his dog, Canis Major. So here is the dog. I don't know if you see it. I can almost see it. That's a dog. And this is the hunter. It's Orion. Okay, and he's got kind of a, anyway, and he's got a sword hanging down here from his belt. But here you get a sense for how bright these stars appear. Okay. All right. Well, that's a good place to end it. We'll pick up here. Again, I'll see if I might want to knock this part out on Friday and then do something. So come and see. I don't know.